All right, now we're going to go over Chapter 2, which is the chemistry of life. If you're wondering why we need to go over chemistry in an intro to biology class, it's because all living things and non-living things are made up of atoms with chemical bonds. So we know that organisms are chemical machines. We have to know chemistry in order to understand biology, at least on some level. And it's important to note that the beginning point for this is that any substance in the universe that has mass and occupies space is comprised of matter. All matter is made up of atoms. When we're talking about these terms, the terms mass and weight are often used interchangeably, but they do have slightly different meanings. Mass is how much substance is present. Weight is how much force gravity exerts on that substance. And that's the reason that our mass is going to stay the same whether we are on the Earth or on the Moon, but our weight will change. So, even though we are 100 kilograms on the Earth, if we move to the Moon, we're still taking up the same amount of space, which means we still have the same mass. Weight, on the other hand, is going to change. And that's because we've changed the amount of force that gravity is exerting on our substance. So that's why somebody who is 180 pounds on Earth will weigh only about 30 pounds on the Moon. All atoms have the same basic structure. They're all composed of protons, neutrons, and electrons. The core of an atom is what we call the nucleus, and that is made up of two subatomic particles called protons, which are positively charged, and neutrons, which have no charge at all. So you could think neutrons, neutral, no charge. Also, surrounding the nucleus, we have subatomic particles called electrons, and these are the negatively charged components of our atoms. You can see the basic structure of those atoms here. Here we have one of our simplest atoms, hydrogen, which contains just one proton in the nucleus and one electron in orbit around the nucleus. Here we have a more complex atom, which is carbon, where you can see we've got 6 protons in the nucleus, 6 neutrons in the nucleus, and then 6 electrons that are orbiting around the nucleus, and that's where our negative charges are. When we talk about atoms, we're usually trying to characterize them either by their atomic number or by their mass number to figure out how they interact. When we look at the atomic number, this is just referring to the number of protons that an atom has in the nucleus. Atoms that have the same atomic number are going to exhibit the same chemical properties and are considered to belong to the same element. So for instance, carbon. There are multiple kinds of carbon, but if they have that specific number of protons in the nucleus, that's what's telling us they're in that element group. When we look at mass number, that is including more than just the protons in a nucleus. We are looking at the mass of protons and neutrons in the nucleus. And that's telling us a lot more information about an atom. Electrons are not considered for the mass number. We're not counting how many electrons are present. And that's because electrons have negligible mass, which just basically means they don't have enough mass to really count in this calculation. You could think of it like this. Similarly, our electrons have very little mass, just like our eyelashes have very little mass. So if we compare how much of our mass is made up of our eyelashes, that's going to be about the equivalent to how much mass electrons contribute to the overall mass of an atom. Electrons are held out in orbit around the nucleus. So you could think of them being held out kind of like a balloon, like this distance away from this child. You could think of the protons and neutrons as the nucleus here in the center. Electrons are going to always be orbiting out here a fair distance away from the nucleus. We do need to remember that protons and neutrons are what determine the mass of an atom and therefore the mass number. And electrons are not useless. Just because they're not contributing mass to the atom, that doesn't mean they don't have a purpose. They're actually the main thing that determines how an atom is going to react and interact with other atoms. It's going to determine what kind of bonds can be formed and what kind of molecules can be formed from different atoms combining. So knowing that, we can ask, what is the atomic number of carbon by looking at this? So if you could just look at carbon for a second and answer to yourself, what do you think the atomic number is? If you answered 6, you'd be right. We have only 6 protons, and that's the only part that matters for determining the atomic number of this atom. So there's our 6 positively charged protons, which determine our atomic number. Now we could look at the same picture and ask, what is the mass number of carbon? Just by seeing the structure of this atom, you can tell it has a mass number of 12, because we have 6 protons and 6 neutrons in the center in the nucleus. Electrons are associated with the energy of an atom, and they have something called potential energy, which means they have the ability to interact. Electrons occupy energy levels, which are also known as electron shells of an atom, which are actually complex three-dimensional volumes of space that we call orbitals. So you could think of just kind of layers that electrons are able to orbit a nucleus, and there's like the first layer, the second layer, the third layer, and so on. And the orbitals are where our electrons are most likely to be found in existence around the nucleus of an atom. So think of it as the pathway that electrons are taking to circle around the center of the atom. Electron shells have specific numbers of orbitals that may be filled with electrons. And to go much further than that, you are on more of a chemistry path than a biology path. But it is important to mention, and atoms that have incomplete electron orbitals are going to tend to be more reactive, because these atoms are looking for a balance in chemical charge. And if we've got an empty spot for an electron in one of our orbitals, say we should have 4 electrons in our outer orbital, but instead we only have 3, that's going to make that atom more reactive, because it's trying to find balance. You could think of it like whenever you put clothes in your washing machine and they're all bunched up on one side and you start the load, and then a little while later you hear that bang, 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 bang as it's totally thrown off center and can't really spin in a balanced way. That would be like an atom that is missing an electron in that outer shell. It's thrown off. So we're trying to find balance so that this system can operate smoothly, so that these rotations can take place smoothly, and that's why we're trying to fill the orbital with the exact number of electrons that is specific to that atom. Atoms are going to either lose, gain, or share electrons in order to fill that outermost electron shell. That is the goal. So if you're missing an electron and you're trying to find that balance, you're going to be looking for what other atoms you can bind with to bring in another electron. Just the same, if you have too many electrons and that has thrown your orbit off and kind of out of sync, you're going to be looking for a place to donate one of your electrons. There are also instances where 2 different atoms are going to share electrons so that they can both benefit by having the right number of electrons, and they'll share them, either equally or unequally. These actions we're talking about are the general basis of chemical bonds. It's also worth mentioning that as electrons move to a lower energy level, meaning they're going closer to the nucleus, energy will be released. If we are moving electrons to energy levels that are further out from the nucleus, that's going to require energy. 2 of the main terms in chemistry that tend to be confused, especially early on, like the first test, seem to be ions and isotopes. So it's important to be able to differentiate the difference between an ion and an isotope. When we're talking about ions, that's just meaning atoms that have either gained or lost 1 or more electrons. And as a result, they're going to have a charge. So cations are positively charged atoms, and anions are negatively charged atoms, which means cations have lost an electron, meaning they lost one of their negatively charged components, and anions have gained an electron, meaning they gained another negatively charged component, giving the overall atom a charge. Knowing that, we could look at this picture and I will ask you which one of these three is an atom. Now that you've had a second to look at them, we can tell this is the atom in this situation. You can tell because we've got 4 protons and 4 electrons. Positive charges are canceling out negative charges so that we have no charge, which means we're an atom. Over here, we can tell we have 5 positive charges and 4 negative charges. So we have to consider what the charge of this overall atom would be. If we've got more positive than negative, this is going to be a cation with a positive charge. Over here you can see we've only got 4 protons, but we've got 5 electrons, which are negatively charged, meaning this atom is going to have a negative charge. So here are 2 ions, positively charged cation, negatively charged anion. This is just called an atom because it has no charge at all. We are balanced. When we compare that to isotopes, isotopes are atoms that have the same number of protons but different numbers of neutrons. So pretty much all elements that exist in nature are going to be mixtures of different isotopes. Here you can see isotopes of carbon. So we've got carbon-12, which has 6 protons and 6 neutrons. Carbon-13 is still the same element, carbon, but because we have a different number of neutrons, these are isotopes. You can see all of our carbon have the same atomic number, 6, and different mass numbers as a result of their different number of neutrons. That's all that we're talking about when we're trying to describe an isotope. They have the same number of protons, different numbers of neutrons. And here you can see what it looks like when we're making a sodium ion. So here we have a sodium atom with no charge at all. We've got 11 protons, 11 electrons. Those are kind of balancing and canceling each other out. So we've got no charge on this atom at all. If so, it would be shown here. You could imagine something in the solution that has a stronger affinity to this electron than the nucleus of this sodium atom does. And it pulls that electron off because it needs it more for the balance. It has a stronger pull. So we pull that electron off. Now this same sodium atom is short 1 electron. And as a result, because we lost a negatively charged piece, we are a positively charged atom, which is an ion, a sodium ion. So now we have 11 protons still. That didn't change, but only 10 electrons. And that's how we ended up with this positive charge. Some isotopes are unstable, and they will break up into particles with lower atomic numbers. So ask yourself, if it has a lower atomic number than it did before, what did it lose? Well, we know that the atomic number is just the number of protons. So if we're lowering the atomic number, that means we must have lost a proton. And that process is called radioactive decay. Radioactive isotopes have multiple uses. We use them for dating fossils, and on the complete other end of the spectrum, we also use them in medical procedures. One example of that is the short-lived isotopes that we use as tracers when we're trying to figure out what's wrong in someone's medical diagnosis. Because these isotopes decay so rapidly, they're not going to harm the body, but we're still able to follow them and basically see where the holdup is or where the problem is. You could think of it almost like finding the kink in a hose that's stopping something from happening in our system. And the tracers will go straight to that point so that we can see where the blockage occurs or where the problem is. and because they break down and decay so rapidly, we don't have to metabolize them. So they're not going to be toxic to us or cause us harm because they break down so quickly on their own. A molecule, when we use that word, we're just talking about a group of atoms that are held together by energy, and that energy is in the form of a chemical bond. So once we have an atom that is holding on to another atom and they're bound together, that's a molecule. Then we could keep adding atoms and that's still considered a molecule. So just basically atoms that have chemical bonds connecting them. There are three main types of chemical bonds, and they're shown here. We have ionic bonds, covalent bonds, and hydrogen bonds. We're going to go over the differences between those three bonds, which you're definitely going to want to remember. And then we also have a fourth kind of interaction between these molecules and atoms, which we call van der Waals forces. And these forces are a weak chemical attraction. So they're not strong enough to be considered a bond. There's nothing physically holding these atoms together, but there's an attraction between them that brings them close together. So you could imagine if an ionic bond is like two atoms have a bridge between them and are actually in physical contact. Van der Waals forces would be like if they were just very close to each other and they're not actually touching, but they are drawn to each other. So it is a chemical attraction, but it is not a chemical bond. When we're trying to differentiate between our three chemical bonds, it's really easy to remember which one is ionic because these occur when oppositely charged ions are attracted to each other. So you have to have ions involved. You have to have a positive charge and a negative charge. Covalent bonds are going to share the electrons between atoms. So that is also pretty unique and makes that easy to differentiate. You could think of how we co-parent. When we're co-parenting, we are sharing the responsibility for parenting, and these covalent bonds are sharing electrons between two atoms that need them. When we look at hydrogen bonds, these occur when polar molecules, which we're about to go over, are attracted by opposite partial charges on different molecules. And I'm going to show you what that means. So our ionic bonds involve the attraction of opposite electrical charges. I think that's pretty fair. These molecules are going to be most stable in the crystal form. So a great example of that is just the formation of salt. Here you can see we've got a sodium atom and a chlorine atom. You know they're just atoms because there's no positive or negative charge on them. So they're balanced. They have the correct number of electrons in their outer shell. But whenever we have movement of one of those electrons, we suddenly end up with a chemical bond. So here's an ionic bond where one electron is leaving this sodium and going to this chloride. So now we have a sodium ion and a chloride ion. We started with two atoms. Now we have these two ions that are held together as a single molecule. And you can see over here the structure for that. So here is our sodium ions held together with our chloride ions, and that's what's making up sodium chloride crystals, our salt. When we talk about covalent bonds, these form between two atoms when they share their electrons. So basically we've got two atoms that need electrons and they've decided to share them. The number of electrons shared is going to depend on how many that specific atom needs to fill its outermost electron shell. These covalent bonds are going to be stronger than ionic bonds, which makes sense. You've got so much pull because not only does the atom over here need this electron badly, the atom over here needs this electron badly. So you can see that they're both kind of holding this electron in place, and that makes it a stronger bond. So what we used to have before this bond was made that we're seeing here, we used to have an H plus and an H plus, two hydrogen ions. Now that we're sharing these electrons, we have a covalent bond between them, and we have hydrogen gas, which is H2. So again, when you're trying to remember which one's which, remember covalent means we have to share the electrons. Another really interesting point that comes up with these covalent bonds is polarity. So some atoms are going to be better at attracting those shared electrons. It's not always shared equally. Just like in co-parenting, how the mom and dad may be working together to parent their child, that doesn't necessarily mean they're working equally to parent that child. You can consider the same thing here. Just because they're sharing, the oxygen and the hydrogen are sharing these electrons, that doesn't mean that they have equal pull. In fact, the pull of oxygen is much stronger. So these electrons are going to spend more time closer to the oxygen nucleus than they will to the hydrogen nucleus. As a result, we're going to end up with something called a partial charge. So when we write out H2O, it's not H2O plus, but there is a partial charge on this end of the molecule and on this end, down by the hydrogens. Because the electrons are going to orbit around oxygen more often and spend more time close to oxygen, that means there's going to be a partial negative charge on the oxygen side. And because there's less presence of electrons by these hydrogen, there's going to be a partial positive charge on the hydrogen side of this molecule. That's what makes it polar. If you need help remembering that, you could think polar like North Pole, South Pole. We're being pulled to one side. It's uneven. So that's what we're trying to say with polar. We're still sharing the electrons, but we're not sharing them equally. We also have covalent bonds where our electrons are shared perfectly equally. So these were two chloride ions. They came together and are sharing their electrons, and they're sharing them perfectly equally. Neither of them has more pull than the other. They have the same composition and the same electrons. So this is a non-polar covalent bond because we're not ending up with a partial charge at all. We have equal sharing between these atoms. When we look at those polar covalent bonds, you can see that oxygen is going to have a stronger pull for the electrons. And since the electrons are not near the hydrogens as much, the hydrogen part of the molecule as much, that part of the molecule is going to be slightly positive. Our hydrogen bonds, our third type of bonds, these are weak electrical attractions that are happening between the positive end of one polar molecule and the negative end of another. So this is about partial charges. If you need to write something down next to hydrogen bonds to just remember what sets them apart, it's polarity and partial charges. So in these bonds, we have partial charges, just like on the water we just looked at. And that is basically acting like a magnet to bond weakly to another polar atom with an opposite charge. The additive effects of lots of hydrogen bonding interactions can also add collective strength to those bonds. Here's a great way to look at that and kind of visualize what we're talking about here. So here is our water molecule. Yes, this hydrogen is held to this oxygen with a covalent bond, but the hydrogen bond is happening here between the water molecules. So because we have a positive negative charge by oxygen and I think I said positive negative. I'm sorry. Because we have a partial negative charge by this oxygen, we have an affinity to bind with a hydrogen bond to the opposite end of this hydrogen on this water molecule. So you can see our partial negative side of this water is binding to the partial positive side of this water molecule. And that's really all we're talking about with our hydrogen bonds. We have polar molecules with partial charges, and that's what's making it possible for these bonds to happen. There's just enough of a negative charge here and positive charge on this side for this hydrogen bond to take place between our water molecules. Water, as we know now, is a polar molecule, and water can form hydrogen bonds. Hydrogen bonding is going to give lots of different special properties to water that other substances don't have. That's because of the hydrogen bonding. One of those properties is heat storage. So water temperature is going to change very slowly, and water also holds temperature very well. When we look at ice formation, that's where we can see few hydrogen bonds will break at low temperatures. That makes the bonds very strong. So when we're at low temperatures, our hydrogen bonds are stronger, and our water molecules are also held further apart because that water is becoming less dense as it freezes. We also have a high heat of vaporization. So water is going to require a lot of energy in order to vaporize from a liquid into a gas, and that's because those hydrogen bonds have to be broken for that to happen. When water does vaporize, it's going to take that heat energy with it, and that's what allows for evaporative cooling. You can see here we have our liquid state water and the weak hydrogen bonds that are holding the water molecules in this arrangement. You can see we've got slightly positive hydrogen to slightly negative oxygen. Again, slightly positive hydrogen to slightly negative oxygen. Once we lower the temperature, suddenly we have increased the stability of those hydrogen bonds. We're holding those molecules further apart and in a more fixed way, and that's when water has become a solid state, like ice. Water molecules are going to be attracted to other polar molecules. It makes sense. The polarity works so well together. If we have a slight positive and a slight negative, that's like puzzle pieces that fit together and magnetize towards each other. So whenever we're talking about water molecules that are attracted to other water molecules, that's called cohesion, which is basically what caused all of these smaller drops of water to come together into these larger drops of water. That's cohesion. Just the affinity of those polar ends of those H2O molecules to come together and create these hydrogen bonds. Cohesion, you could think of like together, think water molecules are coming together with water molecules. Adhesion, you could think we're adding something to water, if you're trying to remember the difference here. Because this is when polar molecules that are not made up of water stick to a water molecule. And again, that's just because of those partial charges of polar molecules. So that's what's happening here with this water spider that's able to walk on the surface of water. It's as a result of adhesion. The polar molecules of the water spider's feet and the affinity that they have for the polar molecules of water. In a solution where water molecules tend to form, water molecules are always going to want to form the maximum number of hydrogen bonds possible. And that makes sense. They all have the same composition, and they all match well, so we have no real reason to stop or to only bond half of the water molecules in a solution. They're all going to fit together like puzzle pieces because every molecule has a positive side and a negative side. When we think about what substances are able to dissolve in water, that's still just determined by polarity here. So hydrophilic molecules are going to be attracted to water and will dissolve easily in it. That's because these molecules are also polar, so they have those same kinds of partial charges on their molecules that will allow them to bond easily with our water molecules, with those hydrogen bonds. We call them hydrophilic because philic comes from Latin for loving, so water-loving molecules. You could think of this like sugar. That is a hydrophilic molecule that will dissolve in water because it is also polar and is able to meet the needs of those bonds between water molecules and the solute, the thing that's being dissolved, the sugar. When we talk about hydrophobic molecules, you could think of that word like fear, like arachnophobia is a fear of spiders. Hydrophobic is like a fear of water. So these hydrophobic molecules are going to be repelled by water and they will not dissolve at all. So this is like oil. It's the reason why when you add oil to water, you can't really see them coming together at all. They stay completely separate. It's because oil is nonpolar, and so there's no way to meet the need for those partial charge bonds because the need is already met in this nonpolar molecule. If oil is nonpolar, it's not looking to gain an electron or donate an electron. It's already in that balance, so it has no need to form hydrogen bonds. Here's a look at how salt dissolves in water. Salt is also a polar molecule. We've got sodium ions and chloride ions that have come together into one molecule, sodium chloride. Once we add those to water, the partial charge of oxygen is going to be attracted to those sodium ions because sodium ions have this positive charge. And we know there's a partial negative charge on oxygen. So if we surround the sodium ion with the oxygen side of our water molecules, that's going to pull those apart. And then on the other side, we've got our chloride ions, which are negatively charged. These water molecules have their partial positive down here by their hydrogens, and those are the ends that are all facing the chloride ion so that they could share their electrons. And that's how we have dissolved this salt in water. If this sodium chloride was totally nonpolar and there was no real difference, then the water molecules wouldn't have partial charges that are able to attract these chloride enough or the sodium enough to pull them apart and actually dissolve them. But they're polar, so it works out. The covalent bond within a water molecule is going to also sometimes break spontaneously. So this is just kind of an observed thing that happens. At times, H2O water molecules will break apart into their components of hydroxide and hydrogen ions. There should be a little minus right here, like there is right here. Because this hydroxide has a negative charge, it's an anion, and this hydrogen atom has a positive charge, so it's a cation. You will need to know those, so you should know when H2O breaks apart spontaneously what we get. A negatively charged hydroxide ion and a positively charged hydrogen ion. The amount of ionized hydrogen from water in a solution can be measured as pH. So I feel like we've all heard pH a lot. We know that that's a scale of acidity, but what we're actually measuring is the amount of those positively charged hydrogen ions. That's why it's the pH scale. Also, the pH scale is logarithmic. So that means whenever you change from, it's a scale of 0 to 14. And if you go from 0 to 1 or 1 to 2 or 2 to 3, that's not really representing a difference of 1 because it's scaled. So it's actually representing a 10-fold change with each change in number. You can see over here, it's not a difference of 1, it's actually a difference of 10 to the power of 1. So, when we look at this pH scale, ask yourself, do you know which side means more acidic? Is it 14? Is it 0? If your answer was 0, you're correct. This side is the acidic side of our pH scale, everything under 7, because that is representing our hydrogen ion concentration. So here you can see this cola, which has a pH of 3, has a much higher concentration of these hydrogen ions than this oven cleaner, which has a pH of 13. You can see there are only 2 hydrogen ions here, and there are 6 hydrogen ions here. So the more hydrogen ions we have, the more positively charged hydrogen ions we have, the lower our pH, which means we're more acidic. Lower numbers, more acidic. 7 is our neutral number on the pH scale. So that's pretty balanced. That's like this bottled water here, where every hydrogen ion is nicely met by a negatively charged hydroxide ion. And so we have that balance where we're neither acidic nor basic. When I say basic, I'm referring to everything that's above 7 on the pH scale. So above 7 on the pH scale means we have a higher concentration of our hydroxide ions. And that is a really interesting example, this oven cleaner. It's a really good one because it makes sense when you think about what's actually happening when we're cleaning the gunk off of the top of our oven. So we know things can get really caked on, and because of the high heat, they're stuck and you really have to work hard to get them off. Unless you go get something like this Easy Off, this oven cleaner, and you spray it on there. So the reason that that's working is because you are providing hydroxide ions with a negative charge to pair with the hydrogen ions that are already in the gunk on top of your stove. And that means those bonds have been met. So now the hydrogen ions can easily be wiped off of that surface, even though they were very stuck moments before. It's because you provided something for those hydrogen atoms to bind to in this solution of this oven cleaner. Similarly, whenever we have kind of acid reflux and we feel really bad and we know we're acidic, our stomachs are acidic and we feel bad and we want to feel better, we might go to Walgreens and get some Tums. Again, that's doing the same exact process, just with a different substance. Now, instead of trying to provide hydroxide to the gunk on your oven, you're trying to provide hydroxide to the acid in your digestive system. The Tums are very basic, so they are similar to baking soda. They have enough of those hydroxide negatively charged anions to pair with the excess hydrogen ions that are making you feel so bad because you're feeling too acidic. So this is a kind of a representation of the pH scale. You should remember that 0 is the more acidic side, 14 is the more basic side, and you should definitely remember that we're really talking about the hydrogen ion concentration when we're talking about the pH. As we just said, pure water has a pH of 7. That means that there are equal amounts of hydrogen ions and hydroxide ions. And any substance that's going to dissociate in water and increase the amount of hydrogen ions is going to be acidic. So these acidic solutions will have pH values below 7. 7 down to 0. Those are acids. Our bases are any substance that are going to combine with hydrogen ions when they're dissolved in water. Basic solutions are always going to have a pH value above 7, so from 7 to 14. The pH in most living cells and their environments is fairly close to 7. Proteins that are involved in metabolism are very sensitive to any pH changes. And because of that, organisms use things called buffers to minimize those pH disturbances. So a buffer is just a chemical substance that's going to take up or release hydrogen ions. And that's just like the Tums that we just talked about. That's an external buffer. That's a buffer that you went to buy. So we also have cellular buffers, substances in our own cells that are providing balance between the amount of hydrogen ions and hydroxide ions. So if we have buffers, that means we have a substance that can take up or release those excess hydrogen ions so that we can keep a balanced pH. And that's it for Chapter 2. Thanks for tuning in, and next we're going to go over Chapter 3. I hope you guys have a good day.